Thank you, John, for that wonderful introduction. And good evening, SACNAS. I'm delighted to be here and share this wonderful evening with you where we commemorate 40 years of strengthening the nation through diversity, innovation, and leadership in STEM. I want to especially thank the organizing committee and particularly Professor and President Maggie Werner-Washburn for her friendship, encouragement, and unflagging commitment to the cause of inclusion and empowerment for Hispanics in the sciences. I also want to take this opportunity to acknowledge two very special women from Davis here. First is Professor Karen McDonald. I think Karen is over here somewhere. Karen, can you raise your hand? There she is, way over there. Karen is here. She's a professor of chemical engineering, and she's here in her new capacity as faculty director for the NSF Advanced STEM grant that we just received last year at UC Davis. The advanced grant is designed to transform UC Davis into an institution that encourages women, particularly underrepresented women, Chicanas and Latinas, to pursue careers in the STEM sciences. And so if you have any questions, if you're a postdoc, graduate student, assistant professor, want to know more about the STEM program, please contact Karen McDonald. Second, I want to acknowledge my lovely wife of 44 years, Wendy. Right there, Wendy, yes, right there, sorry. Who's been a constant source of support and encouragement throughout my whole career. She's seen the good, the bad, and the ugly, and she will give you the backstory on everything I say tonight. 40 years is a long time, and I think in order to really fully appreciate how far this organization has come, it might be worthwhile to take a minute just to reflect on what happened. What were the major events in 1973? The U.S. Supreme Court ruled on Roe v. Wade and overturned state bans on abortion. Genetic engineering technology was invented in the Bay Area in Northern California. The first personal computer was launched, and Motorola made the first cell phone call. The American Indian movement occupied Pine Ridge Reservation at Wounded Knee in South Dakota for 71 days. Chicanas belonging to the Comisión Femenil Mexicana Nacional held their very first conference in Goleta, California. The CFMN was instrumental in ending sterilization of Hispanic women who were unable to read informed consent forms printed in English. In 1973, less than 1% of the 15,000 PhDs that were awarded nationally went to Hispanics. According to the leyenda of SACNAS' founding, in 1973, a small group of Chicano and Native American scientists conceived the notion of a society for the advancement of Chicanos and Native Americans in science in an elevator at a national meeting, a scientific meeting. Now, I've heard that the exact meeting, the exact date has long been forgotten, but what's important about that meeting was it really represented an extraordinary act of courageous and bold leadership, not just for 1973, but even for today's standards. One must remember that, like the Black Power movement, the Chicano movement was born out of the turbulent 60s. The term Chicano elicited mixed emotions among white Americans that ranged from confusion to disdain to fear. The word Chicano was not used in the polite company that you would find in the faculty conference room or the corporate boardroom. But this has changed. Nobel laureate Octavio Paz once said about the Mexican psyche, "We oscillate between engagement and withdrawal. between the shout and the silence, between the fiesta and the wake. Well, in 1973, these oscillations must have been in phase because this small, courageous group of scientists let out a shout that signaled the beginning of a fiesta of inclusion empowerment that has engaged mainstream scientific community for the next 40 years. I'm not finished. The renowned anthropologist Margaret Mead once said, "Never doubt that a small group of thoughtful, committed citizens can change the world. Indeed, it's the only way it's ever been done." So I'm here, I am, and you are a beneficiary of this bold act of leadership. And thanks to the SACNAS founders and elders, I want to thank them tonight. I want to thank those who are here in the room, those who could not be here, and those who have passed over to the other side. I want to thank you for helping make my 40 years in science such an enjoyable and rewarding experience. You're probably asking yourself, who is this man and where did he come from? I haven't heard from him before. Well, I'm actually the oldest son of migrant workers from a small town in the Central Valley called San Joaquin. My stomping grounds are from San Joaquin, Mendota, Kerman, Fresno. And thanks to many wonderful teachers along the way, I've grown up to love science. Science is my life. I have science magazines in every room of my house. And I mean every room of my house. I often tell my friends that I'm addicted to data and science is my cocaine. And if science is my cocaine, DNA is my mistress. My old mentor, Herbert Boyer, UC San Francisco professor and co-founder of Genentech Corporation, said this: the DNA made the brain, and the brain has the ability to decipher the structure of DNA. Therefore, DNA has the capacity to understand itself. Well, if DNA can understand itself, it knows that I have been infatuated with it ever since I opened the pages of that October 4th, 1963 issue of Life magazine that featured an article on cracking the genetic code. Those images and those words in that article ignited a flame in my mind that burns to this day, and I don't ever expect that flame to be extinguished. It's been said that experience is not what happens to a man, it's what a man learns from what happened to him. So instead of using our precious few minutes to talk about my background and my accomplishments, I really want to share with you some of the most important lessons that I've learned over the past 40 years on my journey from graduate student to postdoc to professor to inventor to entrepreneur. As a graduate student at the University of California, Santa Cruz from 1970 to 74, I learned not to be afraid to seek out the smartest person in the room or the department and engage them in spite of everything in my being screaming, "I'm not worthy." In my case, I sought out and worked for a brilliant Australian molecular biologist by the name of Rick Davern. And I could tell he had reservations about me, but I was not deterred. Once I embedded myself into his lab, I did not leave it until I had a first author publication in the Journal of Molecular Biology, and I had my dissertation under my arm. It dawned on me recently that my experiences as a graduate student has helped shape my management style and leadership philosophy. Whether it's serving as chairman of the board of my company, Ventria Bioscience, or serving as director of the Center of Excellence for Nutritional Genomics or Global Health Share Initiative, or just getting two countries to agree on how best to sequence the rice genome I've learned this: never be the smartest guy or gal in the room. If you are, your ideas will inevitably be limited by the gaps in your knowledge and your experience and your conscious and unconscious biases and prejudices. I think those are the words for new leadership for the 21st century. I also learned to be prepared for unexpected opportunities and those setbacks which are actually springboards to success. Like most graduate students, I look forward to my qualifying exam with dread, nausea, and like most qualifying exams, I was poked and prodded to the very limits of my knowledge in many subjects. But then one of the examiners laid on the table a scientific publication and asked me, "Have you read this?" And of course I thought to myself, no, I didn't read this. This is not in my field. It was a Nature paper on the discovery by Herbert Boyer and Howard Goodman that when DNA is cleaved by a restriction enzyme called EcoR1, it left overlapping cohesive ends. We call them sticky ends. That finding proved to be the very foundation of genetic engineering tech revolution and also the beginning of the biotech industry. I was given a stinging provisional pass contingent on writing a 2-page summary of this paper. Months later, as I was contemplating postdoctoral opportunities, I ran into Krellin Pauling, Linus Pauling's son, who was doing a sabbatic leave there at UC Santa Cruz, and I asked him his opinion on the big DNA replication labs at Stanford and the East Coast. And I said, by the way, what about this little lab up at UC San Francisco that's run by an associate professor by the name of Herb Boyer? His response was startling. He said, "Ray, you must go to the Boyer lab." It's interesting to think what my life would have been like if I had been given an unconditional pass at my qualifying exam, and that examiner had not laid that paper on the table in that conference room. As a postdoc in the Boyer lab, I learned a number of important lessons about myself. I learned that in spite of the rough and tumble atmosphere of a big city medical center, where dozens of postdocs from all over the world were vying for their slice of fame and glory, I could actually hold my own. I discovered a perseverance and a resilience that, when mixed with a strong work ethic, gave me the strength not only to survive, but to actually thrive in this high-pressure environment. This was also a time when I became good friends and collaborator with Dr. Francisco Zapata Bolivar, who was a postdoctoral fellow from UNAM, Mexico City at the time. Again, seizing on setback, Paco and I spent the year of the infamous NIH moratorium on recombinant DNA that stopped all research, all cloning on eukaryotic DNA. We spent that time constructing and designing more efficient molecular cloning vectors. We called our vector PBR322. This vector, which bears our initials, was not the first vector, but it was most efficient vector at the time, and more importantly, it was the only vector approved by the federal government. It was quickly adopted worldwide, and our paper citing on the construction of PBR322 has become a citation classic, being cited more than 5,500 times. As a professor, I've learned about ethics, integrity, teaching, mentoring, innovation, collaboration, and team science. I learned that you have to follow your own scientific instincts. You do not have to be a member of the good old boys club. You do not have to pledge allegiance to a particular experimental system to be successful. Biology and the DNA that runs through all living things is much grander and more important and more interesting than that. I remember the words of my UC Santa Cruz professor who said, "Life is too short to waste your time on trivial problems. You must work on the most important problems." I took his advice, and over my career, I've pursued answers to this one question: how is the information that's stored in the genome impacted and modulated by external inputs from the environment? That particular question has taken me across several kingdoms, from bacteria to yeast to plants and to humans. Many of my colleagues at UC Davis called me a kingdom crosser, and I am very proud of that. The lesson that I really want to leave you with at this point, that I think is most important, is learning to live and to thrive in the land of no. You know where the land of no is. It's in the laboratory, it's in the classroom, it's in the hospital, it's on the campus. It's any meritocracy where admission and advancement is based on achievement at the highest levels. I know you've heard your mentors talking about learning to say no to all of the opportunities and all the tasks that you'll be confronted with on your career path as a professional researcher and scholar. But what about constantly hearing no? Sometimes I feel like I swim in a sea of negativity and rejection. No, your application is not accepted. No, your manuscript is not appropriate for this journal. No, your grant was not awarded. No, you can't have more lab space. How about this? After a thorough review of your application, I regret to inform you, blah, 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 blah. You've all heard it. And some of you with gray hair like mine have heard it many times. But about 15 years ago, I had this epiphany that no can be good. No prevents us from getting intellectually lazy and creatively flabby. No is like a workout routine that keeps you alert and in shape mentally and scientifically. I've come to believe that if you're not hearing no on a regular basis, you're not pushing the boundaries of your discipline. You're not exploring the edges of your knowledge. You're not walking that ragged edge of creativity. And it's at those boundaries and at those ragged edges that great discoveries are made. I found that if you have a grand vision and a long-range plan, you can endure that daily disappointment that comes with rejection. And if you're hearing no 8 out of 10 times, you're actually hearing yes 20 out of 100 no's. So how much more affirmation do you need? So I want to talk a little bit about the future and the pace of innovation. Today, society is facing some very important, if not ominous, problems, whether it's global climate change, impending pandemics, shortages of food, shortages of fuel, or the emperor of all maladies, cancer. We need a new generation of bold and courageous scientific leadership who are not deterred by multi-investigator, multi-institution, multifaceted global science. We need the adventurer. We need the risk taker. We need the one that's just crazy enough to tackle the toughest problem. And to make matters more challenging, the pace of innovation is amazingly fast, making obsolete the very tools and techniques that we use to do science. The gold standard for the pace of innovation is Moore's Law, which says that the number of transistors on a chip will double every 18 months, leading to dramatic decreases in costs and exponential growth in chips and computers. While Moore's Law still holds true for the semiconductor industry, it doesn't apply to every sector of the economy. Take automobiles, for example. In 1970, a Volkswagen Beetle went 81 miles an hour, got 26 miles per gallon, and cost $2,500. According to Moore's Law, a Volkswagen Beetle in 2013 would go 324,000 miles an hour on 130,000 miles per gallon and cost 5 cents. But Moore's Law does apply to at least one sector of the life sciences, and that's DNA sequencing. DNA sequencing technologies are transforming how we do research and the questions that we ask. The cost of sequencing, a cost which tracked very closely to Moore's Law until mid-2007, is now pulled away from Moore's Law at least by 3 orders of magnitude. Where sequencing of the human genome cost $100 million in 2001, today it costs $10,000 and the price is falling. The cost per base sequence law is opening up whole realms of science and technology that were heretofore inaccessible to researchers and healthcare providers. So many of us expect to see in the next 5 years predictive models for disease based on DNA and other omic data that will allow clinicians to diagnose you as pre-sick. Imagine the doctor walking into the examining room and saying, "Louise, I have good news and bad news. The good news, you do not have type 2 diabetes. The bad news is, according to your genetic profile, there's a 99.2% chance that you will contract type 2 diabetes between the age of 48 and 50. And poor Louise will look and say, what? Imagine nucleotide-specific genome editing that can be used to correct those genetic defects and those risk factors for disease. How about microbiome-based therapies to treat diseases ranging from cancer to autism? How about the ability to predict contagious outbreaks weeks or months before they arrive by sequencing swabs from handrails and door handles at bus stations, train depots, and airports, and then turning around and using that information to design the next vaccine for that pathogen that hasn't actually arrived yet? How about large-scale DNA sequencing projects involving many invertebrate species to map genes involved in consciousness and cognitive functions like attention, memory, reasoning, and decision-making? The implications for this are enormous. All you have to do is watch Iron Man 3. Genome-based solutions to our everyday problems will impact all disciplines of STEM, and it will force biologists, biomedical researchers, healthcare providers to collaborate and cooperate with their colleagues and friends in engineering, mathematics, and computer sciences. And this is going to take a very special kind of individual: the adventurer, the risk taker, the crazy one. I don't know who you are, but I know that the adventurers, the risk takers, the crazy ones are here in this audience. Okay. And in 1973, a small group of Chicano and Native American scientists performed an extraordinary act of bold and courageous leadership. Today, the whole planet is crying out for courageous and bold leadership. Are you, as SACNistas, prepared to answer this call? Thank you. I wish they could hear that in Beijing. I wish they could hear that in Paris and Lima, Peru, to let them know that you're coming. So for those of you who are prepared to take that call, meet that call, and for those of you who are thinking about it, I want to propose a toast to you. I want to say, here's to the adventurers, the risk takers, the crazy ones. Those who are willing to swim those interstitial waters of innovation and lose sight of the shore. Those who are not afraid to cross the streams and go where no man or woman has gone before. Those who have the courage to walk naked in the garden of truth. You can mock them, you can admire them, but one thing you cannot do is ignore them, because these are the people who are pointing the way to a better future. These are the people who are going to be changing the world. I want to thank you, God bless you, and good night.